Find the tangent line to the following. We have x to the fifth plus sine of 2xy plus e to the 3y equals 2 at the point x equals 1, y equals 0. And we have a bunch of options here. What's the answer? It's got to be C. Are you sure it's got to be C? Well, the answer is A. Now, what's the tool to use here? The tool that we need is implicit differentiation. Why do we need implicit differentiation? Well, we cannot solve for y as a function of x, nor could we solve for x as a function of y. It's just kind of hopeless. So I say, okay, good news is we have the point, we just need the slope. So we start with our relationship. We take the derivative of both sides with respect to x. Remember, whenever you take the derivative of something with a y, there's a y prime. So there's two y terms, so it's not surprising we have two y prime terms. Plug in. X equals 1, y equals 0. And a lot of stuff vanishes. You're left with 5 plus 5y prime equals 0, which says y prime is negative 1. That's your slope. We already have the point. And so we get the line. Y equals minus x plus 1. All right. Good. Well, so that was last time. Implicit differentiation. That'll make a small comeback today. All right. Our thought for the day. We should all have a thought. If you always do what you've always done, you'll always get what you've always got. Now, there's a couple of quotes like this. There's one that's often attributed or misattributed to Einstein. You know, the definition of insanity is doing the same thing and expecting different results. And we could even talk about this in terms of sort of the idea of functions. You know, we have this idea. We have a function where we have our input and we have our output. And we say, look, what's true? If you put the same thing in, you should get the same thing out. That's what a function is. Now, why am I bringing this up at this point? We've just had a test. And this is a great time to sort of think about things and be like, okay, am I happy with the result? That's the output. Some people are. And if you're happy, great. Then you found something that works for you. Keep doing it. That's wonderful. But if this isn't the outcome that you want, you got to think about changing what you put into it. Now, this means change your strategies. You know, how do you study? How do you prepare for tests? How do you learn? And this is a wonderful time to start. The next exam's only about 3 weeks away. So it's time to start getting ready for it. But the good news is it's a more exciting exam. So, all right. So think about how will you change what you do as you get ready. All right. So goal for today. There's sort of two goals. But the first one I want to talk about is the derivative of inverses. And we're going to do it first from a geometrical point of view. So imagine we have a function. And let's see. It's hard to draw something, but imagine I could draw. So here's this function, y equals f of x. Now, you'll notice I have a dashed line here. That's not just random. That's this line y equals x. What does the inverse function of y equals f of x have to do with this dashed line? Yeah, it's a reflection. So imagine picking it up and turning it over. And that would be the curve. So we have this curve, and now let's see if we can try to roughly mimic it. Here, this is y equals f inverse of x. So there's this nice symmetry as you flip across this line. And essentially what's happening is as you flip across this line, you're swapping the role of x and y. All right, that's fine. But now we're after derivatives. Well, what's one way to think about derivatives? Slopes of tangents, right? So suppose I want to ask the question about the derivative here. Well, I can think of it as there's this tangent line, y equals mx plus b. Well, just like you picked up the function and turned it over, you can pick up the tangent line and flip it over. And if you do that, what will happen? This point will come over here, and you'll get this line here. So the tangent line gets picked up and becomes a tangent line again. So these are both tangent lines. But if this was the curve y equals mx plus b for that line, what is this line? X equals my plus b. Because you swap the role of x and y. That's what happens when you go across, when you take that mirror image across the line y equals x. You swap x and y. So here, if our slope is m, here what's our slope? It is 1 over m, right? Because you want to write y equals something x, right? So the idea is you take this m and you divide. So the slope is 1 over m. Not negative 1 over m. That's something different. That's if you wanted perpendicular. It's just a straight up 1 over. Okay. So here's the idea. If I want to take the derivative of f inverse of x, we say, well, you know what? That's 1 over the derivative of something, right? So if I want to understand the derivative here, at this point, I say, let's find this matching point, find that slope, and then take 1 over that. Now the question is, what goes here? Well, well, you want to say y, sure, which is f inverse of x. And so there's the rule. So the derivative of f inverse of x is 1 over f prime of f inverse of x. All right, and that's the geometrical argument. Tangent lines flip across along with the function that you flip across. There's a second argument. So if you don't like this one, you say, I don't like pictures, Steve. Here's one that's more sort of algebraic. Suppose you start and say, look, I know that y equals f inverse of x. That's the same as saying that f of y equals x. Now pull out the tool from last time, which is implicit differentiation. So take the derivative of both sides. Derivative of x is 1. Derivative of f of y is f prime of y times y prime. And so the derivative, which is another name for y prime, is 1 over f prime of y. Well, but what was y? Y was f inverse of x. So 1 over f prime of f inverse of x. So you can do it, once you understand implicit differentiation, it's very quick to rederive this. All right, so here's an example. Any questions on the theory before I jump into the example? All right. So let f of x equal x cubed minus x squared plus 4x plus 6. And g of x is the f inverse of x, so the inverse function of x. Find the tangent line to the graph y equals g of x at x equals 10. Now, what's the worst possible way to try to solve this function? Try to solve this question. The worst possible way is to say, oh, let's just first find g of x. Don't do that. Is it possible? Theoretically, it is a cubic, and there is a formula for solving cubics. And you probably know the quadratic formula, which, let's say quadratic formula takes this much space. the formula for cubics takes about this much space. And you don't know it. You'd have to look it up. It would be messy. It'd be painful. And we don't want math to be painful. It's math. It should be enjoyable. Okay, so we're not going to solve this by finding g of x. That's okay. So what are we going to do? Well, we're going to think about what's going on. So we know we're interested in our x value, x equals 10. So let's think about our y value. So y is g of 10. Can we figure that out? If we can't figure that out, we're in trouble. That's the same as f inverse of 10. Now, how do you find out f inverse of a value? What does that mean? Well, it means you take your function, x cubed minus x squared plus 4x plus 6, you set it equal to the number, and now you try to solve for x. Now, it might be easy to solve for x. Usually it's not. But there's another tool. It's a wonderful tool. In fact, it's one of the best tools mathematicians came up with. And, it was probably Grog back 40,000 years ago. And Grog was like, ugh, and guess. Yes. So unfortunately, Grog has been lost to history. So nobody gets to claim credit for the tool, the mathematical idea of guessing. So when in doubt, make a guess. Spoiler alert, mathematicians love two numbers. Do you remember what they are? 0 and 1. When in doubt, guess 0 and 1. And if those don't work, just keep in mind, we want things that can be possible. Does 0 work? 0 plus 0 plus 0 plus 6 is not 10. Does 1 work? 1 minus 1 plus 4 plus 6 is 10. Aha! We guessed. X equals 1 works. Woohoo! Now, you don't actually have to say the woohoo part out loud, but that's good news. So f inverse of 10 is 1. So what does that tell us? Our point is at 10, 1. All right. What else do you need to make a line? Slope. Great. So we're going to talk about slope. So we need to do the following. Well, we need to take a derivative. So g prime of x, that's the derivative of f inverse of x. And we say, well, it would be nice if there was a formula for that. There is. It's 1 over f prime of f inverse of x. All right. So that says instead of trying to figure out g prime, we really can figure out f prime. And that seems reasonable, even doable. So what is f prime? X squared minus 2x plus 4. Okay, so if we're after g prime of 10, because we're at 10, according to this, that's 1 over f prime of f inverse of 10. Don't forget to take the f inverse of 10. So you don't want to take f prime of 10. That's not quite right. So it's not f prime of 10, it's f prime of what? F prime of the f inverse of 10, which is 1 over f prime of 1. Right? Because f inverse of 10 is 1. Well, what happens when you plug 1 in? To your derivative. You get 3 minus 2 plus 4. 1 is a nice thing to plug in when you have a polynomial. It's the coefficients. 3 minus 2 plus 4, which is 5. And it's 1 over 5. So your slope is 1/5. So now you've got your point. You've got your slope. So just as a reminder, this is our slope. And so our curve, we have y minus the y value of 1 is equal to 1/5 x minus your x value of 10. You can leave it like that, or you can write this as y equals 1/5 x. Then 1/5 times 10 is a minus 2, but you're adding 1, so this becomes a minus 1. Either works. And there we go, we found our tangent line. Woohoo! Nice! Okay, any questions? Derivatives of inverses, right? Good stuff. Okay, one more example, then we can move to our next topic. Okay. So, we're given that f of x is g inverse of h of x, that f prime of 2 is equal to 5, and we have some information. So we have a table. Find h prime of 2.
10.
10 is a wonderful choice, because the answer is 10. Now, how do you do this? Well, you see that there's an f prime of 2, and you have an f of x. So what's the natural thing you want to do? Take a derivative. So it's like, okay, take a derivative. F prime of x. We apply the rule combined with the chain rule. So you have a function inside a function. So the derivative of the outside, that's the derivative of the inverse function. So 1 over g prime of g inverse with the inside plugged in times the derivative of the inside. All right, so derivative, use the chain rule. And now you're like, well, look, I don't need f prime of x. I need f prime of 2. So plug in 2. F prime of 2 is 1 over g prime of g inverse of h of 2 times h prime of 2. Now, we're after h prime of 2. So we'll move that to the other side. H prime of 2, that's f prime of 2 times g prime of g inverse of h of 2. And now we start figuring things out. Well, we know f prime of 2 equals 5. Here we have something with lots of layers. Work from the inside out. H of 2 is 4. You get that from looking at the table. H of 2 is 4. Now, how do you find g inverse of 4? What do? You don't come to 4. You're not looking around on the row. Where are you looking? You're looking down the column. Where do you get 4 as an output for g? At x equals 6. So g inverse of 4 is 6. So you need to plug 6 into g prime, which is 2. 5 times 2 gives you 10. Now, you'll notice there wasn't a lot of particularly crazy algebra. It's just a matter of, do you know the rules and can you follow it? Be patient. Be patient. Any questions? Are we good? People are taking photos? Yeah. All right. Good job. Woohoo! All right. Well, this was a more exciting problem than I thought. All right, we do have to move on to our next topic because today, this was the warm-up. Now for the main event. Logarithms. The time has come. Logarithms. Now, and in particular, we're after a very special function, the natural logarithm. So if f of x is e to the x, the inverse function of e to the x is denoted as ln of x, or natural log of x. Now, logarithms are pretty nice in certain respects. And if you talk to your parents are too young, your grandparents, you say, hey, when you learned math, did you have to learn logs? And they'll say, oh, yes, those were the good old days. We had the slide ruler. Now, you've never heard of a slide ruler. Probably if you have, you've seen one in a museum. But that used to be all the rage, and they would train students on how to use it. And but it really was just, hey, let's use logs. Now, why do we like logs? Well, there's certain rules for exponentials that turn into nice rules for logs. So e to the a times e to the b is e to the a plus b. The corresponding rule for natural logarithms, or logs, log of a times b is log a plus log b. E to the a raised to the power of b becomes e to the a times b. The corresponding rule for log says log of a to the power of b is b log a. E to the a divided by e to the b is e to the a minus b. The corresponding rule says log of a divided by b is log a subtract log b. Because they're inverse functions of each other, log of e to the x is x, e to the log of x is x. This assumes x is positive. We usually don't care. E to the 1 being e says log of e is 1. E to the 0 being 1 says log of 1 is 0. So all this is stuff we knew before. All right. And other than being a great function, we're really going to lean heavily in to this aspects, these three pieces of the natural log. This essentially says the natural log is a great way for pulling things apart. That's why people liked logs. They said, you know what? I don't like multiplication. I like addition. Logs came and said, I'll trade you. You give me a multiplication problem, I'll turn it into an addition problem. And people are like, woohoo, we love addition. And so that's why logs come into play. And we'll see this pronounced more in a few minutes. Okay, so the derivative of log. Turns out it's amazingly beautiful. So we'll use our implicit derivatives, or we can think about taking derivatives of inverses. So if y is natural log of x, that's the same as e to the y is equal to x. Take the derivative of both sides. E to the y times y prime is 1, or y prime is 1 over e to the y, but e to the y is x. So the derivative of log of x is 1 over x. That's nice. Even nicer is the derivative of natural log of f of x. What rule are we going to be pulling in here? Chain rule. You have a function f inside the log function. So chain rule says take the derivative of the outside part. So the outside is natural log. Now what happens when you take the derivative of the natural log? You get 1 over. So it's 1 over, plug in the inside. So that's where the f of x is coming from downstairs. Then the chain rule says, what else do you need to do? Multiply by the derivative of the inside. And so that's where the derivative of the inside on the upstairs comes from. So it's f prime of x over f of x. So the derivative of natural log is very nice. And in terms of derivatives, this is one that you should know by heart because it's going to get used a lot. Like a lot. And all these ideas here, again, these are things that you should know by heart. This just says logs are good at pulling things apart. And sort of the moral of this is one of the philosophies in math that says, look, if you have a big problem, try to turn it into a bunch of small problems, because small problems are usually a lot easier to do. They are, just sort of that's why we call them smaller problems. And so when we have something that can pull things apart, says I can take a big thing, turn it into a bunch of small things, that's victory for us. That's a wonderful thing. All right, so let's try a couple of things. Some derivatives involving log. All right. The derivative of log of x squared plus 1. What would that be? So with practice, we can start going quick. So if you're taking the derivative of a log of something, it's a fraction. What goes downstairs? The function. What goes upstairs? The derivative, 2x. And you're done. Now, on a side note, Does log of x squared plus 1 equal question log of x squared plus log of 1? The answer? No! Here's the thing. Log loves multiplication. That's like its deal. It's like it really loves multiplication. It hates addition. Addition, it just cannot even wrap its head around. All right. So be careful. All right. The derivative of log of e to the x plus 1 is? What goes downstairs? E to the x plus 1. What goes upstairs? E to the x. Okay, derivative of log secant. What goes downstairs? Secant x. What goes upstairs? Derivative of secant, which is secant x tangent x. Can that simplify? To what? Tangent x. All right. Oops, I forgot parentheses here. What's the derivative of log secant x plus tangent x? Well, okay, why not? Well, what goes downstairs? Secant x plus tangent x, right? Whatever's inside, that goes downstairs. What goes upstairs? Well, so we have secant tangent. And then what do we have here? Secant squared. Well, does the upstairs have anything in common? What does it have in common? I heard a yes. Secant. So secant x times tangent x plus secant x. Downstairs is secant x plus tangent x. Does anything happen? What? That's amazing! Oh my gosh! Cool. This will be something that one day you'll say, oh, that's why he talked about it. You'll want to know this in the future. But you can learn about it now. Okay. How about this last one? What goes downstairs?
Cosine x plus 2e.
Cosine x plus 2e to 3x plus x squared. What goes upstairs?
Negative sine x plus 6.
Negative sine x.
Plus the third x.
6e to 3x. 2x. Yes? Any questions? No. We're good with logs? All right.
Here's what
Now, quick recall. The derivative of x to the power a is a times x to the power a minus 1. Now, we said that's true for all values of a. We actually haven't proven it yet. Give us 5 minutes, we'll prove it. But what about the derivative of a to the power x? Well, that turns out to be a to the power x log of a. And we can use that, we can prove that with the chain rule. Because a to the x, you can replace a by e to the log a. Because e to the log a equals a. That's one of the things we wrote down. Then if you have e to the log a to the x, that's e to the log a times x. So log of a is a number. So just think of it like a number. Think of it like 5 or 2. So now I have e to a number times x. Chain rule says it's e to that number times x. And then take the derivative of that, bring the number down. So that's how the log a comes down. And then you say, oh, well, let's just reverse what we did previously. So this is really e to the log a to the x, which is a to the x log of a. All right, so this is just recall. Because we're going to ask a question. Here's the question. What is the derivative of x to the x? Now, you might say, well, how many x's do you have? You have 2, right? If I think of it, well, if I think of this as my x here, then I have like something to the x power. And so I would apply this rule. And I would say, well, it's x to the x times the log of this term, so log of x. if instead I think about my x as this piece, I have x to a power. And so the derivative of x to a power says what? You know, you bring the power down, x to 1 less power. So the question is it guess 1 correct, or is guess 2 correct?
Yes. I like that. Yes.
Guess 2.
Someone has seen the answer. The correct answer is yes. Okay, so we're going to explain what we mean by yes as the correct answer. So it's actually the case that neither one is correct by themselves. But much like Captain Planet, you know, their powers combined, they are Captain Planet, right? It's that ability to work together. So here's how we'll think of it. Y equals x to the power x. Now, the problem here is we haven't dealt with anything where there's a variable upstairs and downstairs simultaneously. So we'd like to do something. So we start thinking about, is there anything that lets us move stuff around? Do we know of anything at all that lets us move stuff around? Logs. Logs lets us bring stuff from the upstairs down. So this becomes log of y is log of x to the x. Or log of y is x log x. Because we can apply the rules of logs. And the rules of logs says, hey, things come down. All right. Well, now take the derivative. We're going to have to do some implicit differentiation here. What's the derivative of log of y? Okay. Remember, derivative of log, it's a fraction, right? What goes downstairs? Y. What goes upstairs? Derivative of y prime. Equals, what rule do you need to use on this side? You'll need to do the product rule. Two things are multiplying. So derivative of the first times the second, plus the first times the derivative of the second. Now, do we have another name for y? Do we know another way to think about y? Is there anything at all we could call y? Oh yeah, we could call it x to the x. So this is y prime over x to the x equals all this. So that tells us then that y prime, which is what we're after, that derivative, if you multiply it across, well, you're going to get x to the x log x. That's the first term. Plus x, and then here it'll be x to the x divided by x. That's x to the minus 1. So you'll see that we see here is our guess 2, and here is our guess 1. So that's why our answer is yes. In fact, you needed both parts. All right. Well, this is a very simple example of a really cool idea. And that's called logarithmic differentiation. Now, what's the point? The point isn't that logarithms are how we take the derivatives. Logarithms are how we simplify what we're trying to take a derivative of. What can logarithms do? Well, logarithms take things like multiplication to addition, division to subtraction, and exponentiation to multiplication. In other words, it takes harder stuff to easier stuff. So we can make life easy for ourselves. That's the whole point. We are taking a logarithm before we take the derivative so that the parts that we actually have to take the derivative of involving logs are simpler. So, what's the formula? Well, you remember how we said the derivative of log of f of x is f prime of x over f of x? I can multiply the f of x across, and we get the following. F prime of x is the original function times the derivative of the natural log of the function. And that's logarithmic differentiation in a formula. That's it. That's all logarithmic differentiation is. Nothing more, nothing less. Now, when do you use it? Well, if you see this, so in other words, lots of multiplication, division, exponentiation, then you use this. That's it. If you see lots of stuff and like, oh, this looks terrible, I really want to pull things apart, then we use the formula. Okay, so the derivative of x to the a. We haven't actually proven it yet. Let's prove it. Okay, according to this rule, this right here, this is our f of x. So this would say it's x to the a times the derivative of natural log of x to the a. But is there another way to write natural log of x to the a? It's the a comes down, so it's a log of x. What's the derivative of a log of x? Well, the a is a constant. X to the a is still in front. The derivative of log of x is 1 over x. So that becomes ax to the power a minus 1. So that's the proof of the derivative of x to a power. And that works for any power. That's a really slick proof. So as soon as you know how to take the derivative of log and you knew about the chain rule, life was easy. This is much better than what we did before. How about the derivative of x to the a? Well, now this is your function. So that's a to the x times the derivative of natural log of a to the x. But what can you do here? Here the x comes down times natural log of a. Well, natural log of a is a constant. So what's the derivative of x times natural log of a? Well, the answer is that natural log of a. Because the derivative of x times a constant is the constant. So that's the derivation that, we said, oh, yeah, like e to the a is e to the log a, and you do all this work. It's like, no, just do this. And it works. Now, in the interest of time, you take the derivative of f of x, g of x, and you apply logarithmic differentiation, you get f of x times g prime plus f prime g. Which is to say, product rule follows from combining the chain rule plus logarithmic differentiation. So the chain rule is sort of the ultimate rule. Okay, so we have a couple minutes left. That's enough time for us to do a simple cool-down problem. What if you were asked to find this derivative? What should be your tool? And the answer is not like, well, I'll take the 0. No, we don't take zeros. We get all the points. What do you see here? Sorry, what? Yeah. You see lots of multiplication. You see lots of division. You even see a function upstairs and a function downstairs. This is tailor-made for logarithmic differentiation. So you say, well, look, this is the same as x to the fourth plus 2x plus 7, 3 minus sine of x to the x squared over secant of x times the square root of x squared plus 9. Now, where did this come from? I just copied that. Times the derivative of the natural log of the same thing. Now, at this point, you're like, well, you haven't really made life better, Steve. You just added a lot more writing here. But now comes the better part. What can you do? Well, multiplication becomes addition. So I'm just going to put a quotation mark here. So this is the derivative of natural log of x to the fourth plus 2x plus 7 plus x squared natural log 3 minus sine x minus natural log secant x minus 1/2 natural log x squared plus 9. Now, question. Would you rather take this derivative or this derivative? The second one, because we are reasonable, smart people, and because we love ourselves. We want to be kind to ourselves. And so, of course, we take the second one. And so we say, okay, so what happens? Again, you just copy the part in front. And you say, the derivative of natural log is always easy. What's inside goes downstairs. Derivative goes upstairs. Product rule, 2x times the second term plus x squared. Downstairs, 3 minus sine x. Upstairs, negative cosine x. Derivative of log secant. Downstairs, secant. Upstairs, secant tangent. Log of x squared plus 9. Downstairs, x squared plus 9. Upstairs, 2x. And essentially, we're done. We've taken that derivative. We could clean up a little bit, but we don't need to. No. All right. Normally this is where we throw up our final problem. Okay, so let's look at it. 30 seconds. Any gut feelings? Oh, good gut feelings. 1/2. 1/2.